Let me just.
All right, welcome everybody. I think I know many of you. I'm Christine Jones, and I have the pleasure of introducing our second Steve Murray Distinguished Lecturer to you, and that's Ryan Hickox, who I think many of you know because he was a graduate student here. I learned pretty much everything I know about AGN when I was working with Ryan on his thesis. Before he came here as a graduate student, he was an undergraduate at Yale. And he seems to really like these Ivy League schools because, after he finished at the Harvard Ivy League school, he turned down a Chandra fellowship and went to Durham for a postdoc. But then he came back to his third Ivy League school, which is Dartmouth, where he's now an assistant professor. And he's got a nice Sloan fellowship there. And Dartmouth has recently decided that they're going to adopt the house systems that they have at Harvard and at Yale. And they've named 6 house professors for these. And Ryan is now one of them. So he has that too. So he's going to talk to us today on the hidden monsters, obscured AGN in the era of Chandra, NuSTAR, and WISE. There you go. Thanks.
Thank you. Cool. Is that working okay? Can everybody hear? All right. Great. Well, thank you very much, everyone, for having me. It's a real pleasure to come back here. I think the last time I gave a talk of any significant length in here was my PhD thesis defense, so it's all kind of flooding back to me now. Anyway, I'm actually going to talk about stuff that has its roots in my PhD in ancient history, so that's good. So the first thing I'd like to do, of course, is just to say thanks to Steve. This series is in memory of him, and he was really a really important influence on my own development as a scientist and as a member of the research group. Christine was my nominal advisor, but I really worked with Bill and Steve in particular very, very closely throughout my PhD and beyond. And so, we miss him. But I hope that we can do something to continue to build on his amazing scientific legacy, along with everybody else who had so much to do with the building of Chandra. And I'll highlight a few of the results that he worked on and that we are sort of continuing as we go along. I also should mention I was really sorry to hear about also the passing of Dan Harris this week. So these are I didn't work as closely with Dan, but I have such a strong connection to the whole high energy division here that I'm glad to be able to come back and do things in some of their memory. Anyway, okay. Let's skip over up I-93 and I-89 a couple hours up to Dartmouth, where I am now an assistant professor. I just want to tell you a little bit about the research group that we have there. Sometimes people think of Dartmouth College. It's a college in a small New England town, and so sometimes people think of it as being a liberal arts college like Williams or Amherst or something. But we're really a research university, and there's a lot of great research going on in the Department of Physics and Astronomy there. And in my group in particular, we focus on studying black holes and galaxies. And so at the moment, we have 4 graduate students, 1 postdoc, and there's another one that's advertised right now. So if any of you are on the job market, please look at the job register for another postdoc position. We have a bunch of undergrads working with us as well, and a number of people who have formerly worked in our group, including people that some of you know very well, in particular Francesca. And so I'm going to highlight as we go along. I'll show pictures of each of these people, or most of them at least, and highlight some of the work that they've been doing to show you, precisely what we're doing in our group up there. So in order to motivate the research, I'm going to talk about obscured quasars today, but in order to motivate the research, I want to step out and ask what's the really big picture? And the really big picture is that we want to understand, ultimately, galaxies and cosmic structure. And so this is a really cool animation that I found recently of the, it's a 3D visualization of the relatively local universe as mapped out by the Sloan Digital Sky Survey using their real images. And this gives you really great, I mean, of course, you're traveling much faster than the speed of light here, and there's no relativistic effects. But this gives you a really great kind of intuitive understanding of what actually intergalactic space is like. And one of the things it tells you is the universe is absolutely teeming with galaxies. And it's teeming with all kinds of different galaxies. And so obviously one of the major motivations for astronomical research is to understand where these galaxies come from. What are the processes by which they form and their components form over cosmic time. And so we're interested in very special kinds of galaxies. Here's a regular galaxy, regular spiral galaxy, sort of vanilla looking thing, has sort of a familiar structure. But every once in a while, so most galaxies look kind of like this, but every once in a while when you look at a galaxy it looks like this. And it has a luminous point source in the center of the galaxy that can outshine the light from all the stars in the galaxy put together. And so this is, as you all know, a quasar. Now, we study these things, and I'm going to talk mostly about luminous quasars today. And I think that it's useful sometimes to think about what is the, in intuitive terms, can we actually understand the power output from a quasar? Often astronomical quantities are really hard to think about in some kind of intuitive way. So let's at least give it a shot. So the total power output of a really luminous quasar, volumetric luminosity, is around 10 to the 47 ergs per second. Now let's try to understand that in terms of something that's really powerful and something of which there are a lot on the Earth. So the most powerful explosions we can think of on the Earth are made by humans at least, are a hydrogen bomb. It makes about 10 to the 24 ergs of energy. And there are 10 to the 22 approximately grains of sand on the surface of the Earth. So this is kind of crazy. If you do this calculation, those of you who are good with exponents will realize that every second a powerful quasar, for every grain of sand on the Earth, produces the equivalent of 10 hydrogen bombs of energy. Whoa. This is a really, 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 really large amount of power. And so I think it's pretty neat that we can even observe these things and get to study them. And of course, it's why we can observe them across the whole observable universe, is that they are so incredible. They're the most powerful light bulbs that we know of. And what powers this, what produces this huge amount of energy in the center of the galaxy? Of course, it's a supermassive black hole that lies there. And so just in terms of the general picture of where this power comes from, you have black material accreting onto a supermassive black hole in some kind of accretion disk. It loses angular momentum, loses gravitational potential energy, heats up, and radiates, and sometimes also will produce relativistic outflows, although today I'm really going to focus on the radiatively bright things. And the amount of energy that this can produce is really large. In terms of the fraction of the rest mass energy that comes out as luminosity, in terms of the accretion rate, it's about 10%. And this is the most efficient energy to matter to energy converter that we know of in the universe. And for the PP chain in stars, it's only about 0.7%. So this is another reason why these black holes are so incredibly powerful. So the big overarching question that at least my research group works on, one of the big ones, is simply, where do black holes come from? What is the process that actually drives this accretion that causes some galaxies to become quasars? And so we focus on this a lot. One of the things we did when I was in Durham, this is in front of the medieval Durham Castle where we had our conference dinner, was a workshop in 2010 on what drives the growth of black holes. And it was myself and, where am I? See, Jim Mulaney is standing right in the front as if he was a conference organizer, and I always thought this was a funny picture of that. But if anybody knows Jim. Where's me? Where am I? There I am, right there. Okay. And here's Dave Alexander. Dave Alexander and I co-organized this meeting, and we kind of got a bug for it because now we've been doing a meeting every 2 years ever since then. And I'll show you our advertisement for our latest meeting, which will be next year at Dartmouth. Anyway, so this was a meeting where we basically were trying to understand these overall processes, and it's a big field, and there's a lot of really great people working in this. What is the general, some of the things that we can take away generally from this? Well, one thing we can do is we can use AGN to trace the black hole growth history of the universe. So you can just add up all the growing black holes and convert that to a mass accretion rate, and then look at the cosmic evolution of the growth of black holes, and you end up with a curve that looks like this, which actually follows, if you do the same thing for star formation, they have very much the same behavior. And so that implies that that gives us some indirect connection, the fact that the growth of structures, black holes, and galaxies are somehow connected. They're growing together. Another thing you can do, and this will be important in just a minute, is that you can also use these growing black holes to produce the cosmic backgrounds, and in particular the cosmic X-ray background. If you want to understand where the cosmic X-ray background comes from, we know of it as it was initially detected as this diffuse cloud of high-energy X-rays. You can model this through the combination of a bunch of different growing black holes. And so there have been a number of papers on this. This is one from Tracer et al. From 2009, and what you do is add up all the emission from all these growing black holes that you can detect. And you find that in order to produce the cosmic microwave background, there are a bunch of unobscured black holes, ones where you're looking right at them without anything in the way, but actually to make it work, you also have to have a whole bunch of obscured and Compton-thick, very heavily obscured black holes. And I'll get into more about what this means in a second, but just to make the point that one of the things that understanding the growth of black holes can do is actually understand the production of this cosmic background. This already gives you a hint, just this cosmic synthesis gives you a hint that most of the black holes in the universe actually have stuff in the way that's blocking your view to them. These are these obscured and Compton-thick ones. And indeed, we know that most AGN in the universe, if we look around us, are actually obscured by dust. And we're starting to learn, and I'll give you some pieces of evidence for this, we're actually starting to learn that a half or more of even the most powerful luminous quasars are hidden by gas and dust. So here's 3C273, famous unobscured quasar. This is an obscured quasar at high redshift, and you can see they look very different. There's something that's blocking the optical light. It looks just like a normal galaxy. And it turns out there are an awful lot of rapidly growing black holes that if you looked at them in the optical, for example, they would just look like a normal galaxy. And so one of the real aims of this research is to tease out how much of this hidden black hole growth is there, and how is it connected to other cosmic processes. In particular, one thing, so I'll show you a bit of evidence about how we detect growing black holes and how we know that about half of them are obscured by gas and dust. But an important question that immediately comes out when you start thinking about this is what is actually causing this obscuration? There's some stuff that's getting in the way of your view down to the central engine of the black hole. And there are really two general ideas. One is that you have a structure on the scale of the accretion itself, sort of on parsec kind of scales, that it takes the shape of some kind of approximately axisymmetric torus, although we really don't know what the details of that are. But in this case, whether or not it's obscured just depends on your viewing angle. If you look down the pipe at the accretion disk, then it's unobscured, and if you look along the torus, then it's obscured. So there's a lot of evidence that local Seyfert galaxies, for example, the obscured ones are obscured by a torus like this. However, there's also a possibility that galaxies running into each other or otherwise having a distribution of gas and dust in them can obscure the black hole. So you're actually looking through a larger scale distribution of gas or through clouds superseded along your line of, or superposed along your line of sight. And so this is a simulation that gets showed a lot sort of as one illustration of this. This is a simulation of two disk galaxies running into each other, showing the gas in those two disk galaxies. And basically what happens here is the galaxies run into each other. There are torques that cause some of the gas to go down into the center of the galaxy and can actually produce accretion onto the black holes. And this whole process terribly mixes up the gas distribution in the galaxy and can produce a large, dense covering fraction or covering factor around the black hole, so that at various phases along here, if you were to observe a growing black hole, it would be obscured from any line of sight, or at least would have a large number of obscured lines of sight. This particular simulation also includes black hole feedback, which I'm not really going to get into much in this talk, but then showing how the black hole can actually expel some of the gas, given the assumptions in this model. Anyway, the point is that this gives you basically another picture for how obscuration can happen, which is that somehow you have a obscured quasar that's either obscured on a small scale or on some kind of larger scale, and then eventually blows out the material, and that perhaps is associated with a merger or some other large dense gas distribution. Okay. So these are the pictures that we want to test. And we want to sort of understand the whole process behind this, or all the physical characteristics behind these hidden black holes. And so I'm going to go through in this talk today, I'm going to go through sort of three main questions that we want to ask. First is obscured quasars. I'll be focusing mostly on the quasars, the most powerful black holes with bolometric luminosities of, say, 10 to the 45 or higher, or per second or higher. And so the three questions I'm going to address are: how do we find these obscured quasars in the first place? How heavily buried are they? And what are their host galaxies and large-scale structures? And hopefully I'll address each one of these by the end. These are all really interesting questions, and they're interesting enough that we're going to have a whole meeting on them this next summer at Dartmouth from August 8th to 12th on the Dartmouth campus. We're just getting the website and all the stuff, the SOC and everything put together for this. But if you're interested in this kind of thing, and especially if you're around here, it's really easy to come get to us. Please consider looking out for an abstract for this. And so this is something we're very much looking forward to. I should mention before I get going, in the title of the talk is Obscured Quasars in the Era of Chandra, NuSTAR, and WISE. And I would just want to focus on particularly these three observatories and how they help us learn about obscured black holes. Chandra needs no introduction, of course, to this group. All of you guys are well aware with how Chandra can be used to study all kinds of AGN. And I just want to highlight again the contributions of so many people in this division who actually helped build Chandra. An exciting new development. I initially didn't include Chandra in my title because I think about it as something that's just kind of always been there. But of course, I got here in 2002, so Chandra has not always been there. NuSTAR is the new observatory that launched in 2012. And this is the first focusing high-energy X-ray observatory. So it's much less sensitive than Chandra, but its effective area extends all the way out to 79 keV. And it has this sort of interesting expandable, deployable mast with this cool design. And the big thing is that compared to previous hard X-ray telescopes, it has a much, much better point spread function, and therefore is much more sensitive to especially extragalactic objects. And so I'll show you some. Because obscured AGN sometimes have very hard X-ray spectra, this is a really powerful observatory for studying them. And then lastly, the other big observatory that has changed the game recently in this is the Wide Field Infrared Survey Explorer, which performed a sensitive all-sky survey in the mid-infrared that could detect more than 1 million quasars, among the many, many other things that it detected. And I'll show you how this can be used to really break open our study of the obscured quasar population. So, first, how do we find obscured quasars? Well, we go and look for AGN among the galaxy population. This is Steve Murray made this figure ages ago, and I still show it all the time because it's a great illustration of finding AGN in among galaxies. So we take our telescope and we go observe these, and we look for where the growing black holes are. How do we actually find them? Well, there are a number of different techniques, and so this is kind of a busy plot, but it's a good one from a short conference proceedings by Christian Vignali from last year, suggesting, let's say you have a AGN with a torus around it. What are the ways that you can find a obscured object? Well, one is you can look for optical emission from a region lit up outside the torus. This is the narrow-line region. You can look from X-rays, either from the source itself that can penetrate the torus, or X-rays that reflect off of the torus. And then you can also find, use mid-infrared selection to pick up the reprocessed light from the torus itself. I'll go through each one of these, and each one of these is very important for understanding the whole obscured quasar population. So the first one, this is sort of, in a lot of ways, actually probably the oldest way of finding obscured quasars is looking in the radio for radio loud ones. But so I want to sort of mention that that's something that people have done, but I want to focus on the radio quiet ones that tend not to have jets in this talk. So one of the oldest ways of doing it is to look in the optical, and so look for there's long known separation between type 1 AGN that have a blue continuum from the accretion disk and broad emission lines, and type 2 AGN that have only narrow high excitation emission lines. And what's going on is that if you look down the pipe, you see the accretion disk and all the fast-moving gas in the broad line region, whereas if you look through in some obscuring material, you can only see the more extended excited gas, and that gives you, for example, bright oxygen-3 emission. A lot of people, the study of obscured quasars has basically been take this and scale it up to really luminous systems, and that was first possible on a large scale with the Sloan Digital Sky Survey, and here are some papers that have found luminous obscured AGN in the Sloan Sky Survey. But even the largest samples here are only, say, about maybe less than 1,000 in the total number of obscured quasars they can find. So what's another way of finding them? For one thing, this is limited generally in redshift. You have to be real sensitive to pick up these narrow lines, and you have to go into the near infrared to find them once you get out to high redshift. So if you want to actually expand things to higher redshift or over maybe down in luminosity a bit, then one way to do it is with the X-rays. So how do we identify an obscured quasar in the X-rays? Well, the idea is you can take an unobscured AGN spectrum. This is from a cosmic background synthesis model paper by Roberto Gilli, who you saw a couple weeks ago. An unobserved spectrum like this, if you add hydrogen column, this is just the log of the hydrogen column density in centimeters, inverse square centimeters, then what happens is it preferentially absorbs soft X-rays and begins to harden the continuum that you see. So you get less soft X-rays relative to hard X-rays. And eventually, if you become very heavily obscured, Compton thick, meaning that the cross-section to, or the optical depth to Thomson scattering is more than 1, then you actually get down into a regime where you start to suppress even the high-energy X-rays into 10 to the 24 or 10 to the 25 per square centimeter. And so this is an example. This can be used, the spectral shape can be used to identify heavily obscured AGN, and this is an example of a high redshift quasar, redshift 5, that was identified by Roberto Gilli in this quite ratty-looking Chandra spectrum that is identified due to its spectral shape as a heavily obscured quasar. And there's a vast literature on using the X-rays to do this. The last technique, in a lot of ways the most powerful, is using the mid-infrared. So this is a plot showing two different spectral energy distributions for mid-infrared bright sources. So basically you want to look for the emission from this torus, but the problem is you have a bunch of star-forming galaxies around that also emit in the mid-infrared, and you want to be able to tell the difference between them. Thankfully, the hot dust around a quasar has a characteristic power law like SED in the mid-infrared, whereas the a star-forming galaxy has a peak in the near mid-infrared due to stars, and then a colder dust peak out here. And so if you can look in this part of the spectrum, you can tell the difference between a quasar and a star-forming galaxy. And this is something we did, and it was done in a number of papers. These are actually old references now. And one of them was one of the papers in my thesis. So now we're going all the way back to ancient history. The interesting thing is if you do this, if you look at the signatures in the mid-infrared, you find a whole bunch of galaxies that have these signatures in the mid-infrared. And about half of them, if you plot a spectral energy distribution, are really bright in the optical too. They have this sort of smooth power law like SED, and they have, if you look at them in images, they look like bright blue points. So these are unobscured quasars. But a whole other set of them are actually very red in the optical to mid-infrared color. And if you look at them, their images, they're extended. They look like galaxies. And so this is you can distinguish between these two and select both obscured and unobscured quasars using this infrared technique. And so this allows you to find large numbers of them. And this is the sample that we found in my thesis here that included about 700 of each. And so and there's been much more work on this since then, but this immediately gave us some evidence that for the most powerful quasars, about half of them are actually obscured by dust right away. We worked that out. And that is, in a way, a lower limit because some of them are so obscured you don't even see them this way. What we've been doing recently is taking this same kind of selection and extended it to Ys. Now, you will notice the difference in RA and DEC scale between this field, which is Bootes, the 9-square degree field, and this field, which is a part of the SDSS North Galactic Cap. Here we have about, say, 1,000 objects. Here we have a couple 100,000 objects. And so we can now study, using Ys, we can do exactly the same kind of color selection we did before, but now do it with vastly larger numbers. And this is really the way in which Ys has broken things open. And so I'll show you some statistical studies that use this that vastly improve what we got from Spitzer. And there's still a lot to do in the future. But this is really cool. It's sort of like when Sloan and 2DF came out and started doing really large surveys of optical quasars. And all of a sudden, the statistics became such that you could do really exciting stuff. The same thing is true of WISE now for the obscured population. Now, the first thing you have to do, of course, when you're studying these is try to characterize them in some way. The obscured quasars are pretty faint, so in the optical, and so it can be hard to get redshifts for them. For example, Sloan doesn't have that many redshifts for them. And so it's expensive to follow up all of them, but we've been following up a subsample of them to try to understand their redshift distributions and their properties. And so this is something that my group has been actively doing. Kevin Hainline, who now works for the JWST NERCAM team, but he was with us until this fall, he did a survey with the Southern African Large Telescope, which Dartmouth has a big share on, and this is just a sample of the bunch of WISE selected quasars that he observed. And so A, we identified redshifts for them. B, we could put them on an optical line excitation diagram and show that indeed these things actually are in the optical. We identified them just based on photometry, but in the optical they really are AGN. We also could make spectral energy distributions for them, and these look pretty familiar. They look like this SED here, where you have a galaxy and a obscured AGN. Likewise, you have a galaxy and a reddened AGN. There's been a lot of work. We're not the only group doing this. There's a really big survey using a slightly different selection by Mark Lacey and his collaborators. And so together we're all sort of building up this large sample of well-characterized obscured quasars, which you need to do a whole bunch of different things in order to study them. And one of the things we want to do is get photometric redshifts, and by using these to calibrate photoses, and this is something that my grad student Chris Carroll is working on. It's a really challenging problem, but he's getting there. So how do we find them? Well, we find these AGN based on the X-rays, or the optical, the X-rays, and in the mid-infrared. The next thing we want to understand is how heavily buried are they? Actually, how deep are they? What is the level of obscuration? And of course, to an X-ray astronomer, that means what is the hydrogen column density? And so there's a lot of different ways to do this, but the X-rays really provides, in many ways, the best handle on this. It can be hard, really hard, based on SEDs, to tease out the exact level of extinction. So there's a certain amount of reddening on this nuclear component, but it's very degenerate with the sort of input shape of the AGN spectrum, and often you only get a lower limit. And so the X-rays are a really powerful way to do this. And so what we've been doing is doing X-ray studies of obscured quasars to try to directly characterize their obscuration. And so one of the studies on this was done. This was done with Steve Murray and a student of his at Hopkins, Sean Usman. And what we did was looked at our wide field booties, the XBootes survey, and looked at regions that had been observed more deeply. This shows all the ACES I pointings. There are also some ACES S pointings in here that are not shown in the map. But we found a bunch of those obscured and unobscured quasars that I selected and I showed you from my thesis, ones that were bright enough in X-rays to do X-ray spectral fitting, and did a X-ray spectral fitting of those. And what we get when you get out the obscuring columns is that the bulk of the optically selected objects have very low obscuration, whereas the bulk of the optical to infrared objects that look unobscured, they also are not obscured in the X-rays. And the bulk, pretty much all of the ones that are obscured in the infrared and the optical are obscured in the, do show obscuration in the X-rays. And the correspondence here is very good. If you include the ones in the middle that we're not really sure about based on the constraints, the correspondence is excellent. It's better than 90%. And so this is good. This A allows us to say that we are identifying obscured quasars using our simple photometric techniques. The other thing that it does is tells us that at least for the ones that are bright in X-rays, these are ones that had at least 150 counts in a 40 kilosecond Chandra observation, that we don't get to that high of obscuration. We get to about 10 to the 23. And so the ones that we detect in the X-rays in our like medium depth survey are actually not that heavily obscured. They're a little bit obscured. So this is one thing that we can do, and this was a nice legacy of some of the GTO time and also GEO observations that we did for these objects' booties. Another thing we've done is looked at nearby obscured quasars. This is Markarian 34, and looked at them with NuSTAR, high energy X-rays and low energy X-rays, and tried to characterize their obscuration. So this is a paper by Posha Gandhi, looking at NuSTAR observations, we see this reflection feature that's coming off probably the interior of the torus, and this very hard Compton hump here, plus a bunch of other sort of soft emission in the galaxy. And there's been a number of papers now with NuSTAR that are doing this kind of modeling that really need the high energies in order to be able to nail down the spectral model. We've used the different ones. This is the Brightman and Nandra torus model, for those of you who are experts at this. We also tried my torus and some other ones to try to fit this complex spectrum. And at least for this source, what we get is an NH greater than 10 to the 25 per square centimeter. So this is a really heavily obscured object. And just one example of a few others that we've seen like this. Another technique you can use X-rays you can use X-rays to work out the obscuration. Oops. Uh-oh. I lost my. Just a second. There we go. Another way you can do this, which is a technique that was pioneered really by Dave Alexander about 10 years ago, is to use the fact that the X-rays get attenuated by not so much the spectral shape, but just the fact that they get attenuated by the obscuration, and use another measure of the intrinsic AGN luminosity and compare those two. And so the best one is the mid-IR luminosity, because that tends to have very low optical depth. And so you can measure the LI and the mid-IR luminosity of a quasar, and then measure its observed X-ray luminosity, and the ratio of those two basically gives you some sense of how obscured they are. So these are a bunch of optically selected Sloan type 2 quasars that we observed, some of them with Chandra, and then here are observations with NuSTAR. And the lines and the lines here, or sorry, the points down here are the observed points, and then the lines here correspond to what you would get if you corrected for obscuration. So what the implied intrinsic obscuration is when you can actually directly measure the column density from the X-rays. And here, this line here shows the intrinsic relationship as determined by Gandhi et al. And this is sort of the Compton thick few times 10 to the 24, 10 to the 24 regime here. And so what you find is that these guys are really weak in X-rays compared to their infrared luminosity. And if you imply what that figure out what that implies about their column density, it's mostly Compton thick for these sources, or at least very heavily obscured. And for the ones that you can actually get the column density out directly and correct it, you get back up on the sort of local relation. This is true for Chandra, which observed XMM, which observed 2 to 10 keV, but it's also true for NuSTAR, where you notice that the attenuation is weaker at the higher energies, and so in a way you have a stronger lever arm for measuring obscuration with NuSTAR, and yet all these guys are either barely detected or not detected, most of them, with NuSTAR. So also with NuSTAR you get implied that a large number of them are Compton thick. And so, let me go back here and put this plot back up. What this implies is a direct measure of the fact that we're getting a bunch of Compton thick objects among our optically selected quasar or infrared selected quasar samples. And so this is what we determined before NuSTAR, where we had a bunch of things that maybe appeared Compton thick, but if we looked at them with Chandra or XMM, we couldn't really tell. Now with NuSTAR, we have a clear detection of a significant fraction of very heavily obscured AGN. We're following this up a little bit. So the objects that have been observed so far with NuSTAR were type 2 quasars, really luminous optical quasars, or really, really powerful infrared things called hot dogs that were detected with WISE, that are these hot dogs were named by the same group that named mad cows and hush puppies, if you were curious about this, the guys at JPL. These are really luminous, powerful AGN. And one thing we wanted to do was go back and look at sort of more typical WISE-selected AGN, the ones that we observed with SALT that I showed you before. And so this is super preliminary. I probably shouldn't even be showing this. It's hot off the press. But anyway, we have just very recently got some NuSTAR observations of one of a set of 4 of these quasars that we were interested in. Here is an object, the SED of one particular object, and here are the high excitation lines, neon 5, neon 3, that show this thing is an AGN. So we just got NuSTAR observations of it. And drum roll please, and what we see is nothing. We got a 40 kilosecond NuSTAR observation of this guy, and there's nothing there. And so what does that imply? Well, that actually implies something pretty cool. Again, that implies this thing is Compton thick. and actually quite very compact thick. This line is 5 times 10 to the 24. Which, is not terribly crazy considering, in fact, you can see you have very heavy attenuation on the AGN component in the SED. But anyway, these are the limits that we could get to in a reasonable amount of time with NuSTAR, and in fact, we have found it. Yeah, sorry, Paul.
Sorry, I might have missed it. When you said Y selected, was that on Y's only colors or optical versus Y's?
Y's colors and optical versus Y's. Yeah, so they had to be red in Y's 1 or 3.4 minus 4.6, and then they had to be red in G band minus 3. I think it's G, yeah, minus 3.4. Okay, so basically the conclusion to take away is these things are really heavily obscured. So the last piece I want to discuss is what are the host galaxies and large-scale structures of obscured quasars. Well, one of the things we can do is study the star formation. I suggested this sort of evolutionary scenario where there may be a lot of star formation, star-forming gas associated with this obscuring the quasar. And we have a really, really good tool now for measuring the star formation in AGN. It used to be that if you looked at an SED of a galaxy with a bright AGN in it, you were pretty much sunk in understanding the star formation because the AGN just dominates the whole spectral energy distribution. And even obscured AGN will contaminate it and make it hard to tell what's going on. But thankfully, we now have data from, not even around anymore, Herschel, which observes out at high energies, along wavelengths where we get cold dust from star formation, and that is not contaminated by the AGN very much. I mean, there's been a lot of work showing that that's the case. And so now you can study the star formation in AGN host galaxies, and this is something that my grad student Chen did. Here's some more SED fits going from the UV into the far IR, and this data point here in Herschel gives you a handle on the star-forming component. And so he did a lot of work on this. This is distilling a big, long, excellent paper into one slide. But the main thing to take away, what he found using our infrared selected quasar sample, was that as you go up in star formation rate, or as you go up in infrared luminosity, which corresponds to star formation rate, the quasars are more likely to be obscured. So there's an increase in the obscured fraction as you go to higher star formation rates. And at the most luminous star-forming galaxies, it's like 80%. So if you have a quasar in a really powerful star-forming galaxy, it's most likely obscured. This is suggesting something more than just that unified model that I showed before. Another recent result, which is kind of cool, is that when people are looking at the morphologies of obscured AGN with the Hubble Space Telescope, looking for evidence of mergers, when they look at various kinds of obscured AGN, either sort of slightly dust red and broadline quasars or Compton thick X-ray AGN, or at least obscured X-ray AGN, they find that they're obscured. And this is a recent paper by J.L. Kuczewski, sorry, that's spelled wrong, that the fraction of AGN that are obscured goes up as you go to higher column densities. So this is again suggesting that there's something on the scale of the galaxy that's going on. The last clue related to this we could use is something that's sort of completely independent, which is quasar clustering. And so one question is, how are quasars, we've been looking at the properties of their host galaxies, how about the halos that they live in? Are quasars more strongly clustered? Are obscured quasars more strongly clustered? In the unified model, in the sort of torus picture, there should be no difference because it's just orientation. So the dark matter halos that host a quasar, or obscured or unobscured quasar, should be the same. It's possible in various models that if things change with time or go through some evolutionary scenario, that if you have that, then you can have actually galaxy scale structures doing the or interactions doing the obscuration. There could be a difference. So it's interesting to go out and check. How do we measure the dark matter halo masses of objects like quasars? Well, the way we do it is using the 2-point correlation function, which is basically just a statistical measure that allows you to tell whether a population is unclustered or strongly clustered together. And so there's a lot of details in how you actually do this that I will leave aside for this discussion. But just to make the point that from models of structure formation, we know that more massive halos cluster more strongly. And so clustering tells you dark matter halo mass. So if you can measure how objects are clustered on the sky, you can measure their dark matter halo mass. And so this is something we did in 2011 while I was at Durham. We looked at this same sample for my thesis and measured their spatial clustering and found a small difference between the obscured quasars and the unobscured ones. This is actually doing a spatial cross-correlation with galaxies, but the idea is the same. And so then if you ask, what is the, you can actually, this slide, we don't need to worry about this one. If you ask, what is the halo mass as a function of redshift, unobscured quasars had been observed to live in a sort of characteristic halo mass at all redshifts, and our type 1 quasars lived in that space too. But the obscured ones looked like they might be a little bit more clustered. But you can see the errors are pretty big, although there are some systematics that suggest that this could in fact be even higher. So this was a suggestion that maybe the unified model did not apply to these. So what do? Well, we need to reduce the size of the error bars. And the way we did that was to check it with Ys. And so this is something that Mike DiPompeo, our postdoc, did last year. Measured the angular clustering of all these objects that you saw before, and lo and behold, you still see a difference between the obscured and unobscured ones. So this is cool. A lot of people had some questions about this. This was also done by Donoso et al. 2014 that came out just before we did, although there were some issues with the Ys mask in there. They found a gigantic difference between the two, and we realized that part of that was due to systematics, which is something that we're still trying to beat down. Mike's result was a nice, robust, appeared to be robust confirmation of this. However, this is still kind of counterintuitive, and there are lots and lots of challenges with doing these clustering measurements. So we wanted an independent way of measuring it. And so how do we do that? Well, we used a really cool new technique, which is lensing of the cosmic microwave background. So how does this work? Well, you do CMB measurements with, say, SPT or Planck. This is just a little simulation from, I think it's from Wayne Hu's website, showing the background that you would expect in the absence of lensing. And then this is a little bit exaggerated, but showing what would happen to the cosmic microwave background in the presence of foreground large dark matter halos. And so you can deconstruct a CMB lensing, or sorry, CMB map, looking for these features characteristic of lensing, and you end up with a map that looks like this, lensing across the whole sky. So now, of course, well, we expect quasars, which should trace the dark matter. They should be living at the places, preferentially, where there is more lensing. And so you can do this. You can actually perform a cross-correlation of the quasar density map with the CMB lensing map. This is data from the South Pole Telescope, and a pure Ys selected one that wasn't separated into obscured and unobscured. This was a paper by Jim Geach et al. And he made this cool slide that basically shows if you've been up in quasar density, so by design, this is low density, this is the stacked average density of quasars and high density, and then you stack the lensing convergence. Look at this. It's amazing. You have less lensing convergence where there's not many quasars, and a lot, and it goes right through zero. So this is really cool. It works. I mean, I still am always kind of amazed that our cosmological model actually works. This thing, I mean, these are two completely independent measures of this. But this is the more precise way of doing it. This is the cross power spectrum, and you find indeed, and then these lines here are what you expect for dark matter halos, and you do indeed find a difference in the clustering. So, Mike has now done this more carefully using latest data releases of Ys and Planck, looking for all kinds of systematics. And we do find, this is again this plot of halo mass versus redshift, we do find that this is our original data points from my 2011 paper, we do indeed find that there is a difference in the clustering, although it's kind of only suggestively significant. But at least the lensing and the clustering do agree with each other, and that's pretty powerful. And so this is at least some evidence suggesting that maybe some obscured quasars are obscured by some kind of evolutionary process and not just a torus. There are other results on this, though. So Mike's results suggest that obscured AGN cluster more strongly. There are results from X-ray AGN that suggest the opposite is true, at high redshift at least, that the unobscured AGN cluster more strongly. And there are results from low redshift looking at infrared selected AGN that are lower redshift, lower luminosity that suggest there's no significant difference. So we're still this still needs further study, but I think it's really a compelling line of inquiry. Okay, so we've reached the end. So let's just try to answer these questions that, as we raise them. The first question is, how do we find obscured quasars? Well, we detected them in very large numbers, hundreds of thousands of them, in particular using X-ray and mid-infrared techniques. They're often very heavily buried with a large fraction being Compton thick. So this is kind of cool. This is suggesting to us that the X-ray surveys that we've done for a long time to select AGN really are missing some fraction of the obscuration in the universe, and we have to combine all our different techniques in order to try to tease this out. And lastly, what are the host galaxies and halos? Well, obscured quasars are commonly found in rapidly star-forming interemergent galaxies and are in massive halos, probably more massive than unobscured ones. And so that's exciting. And it gives us a lot of potential for testing these evolutionary pictures. So in the near future, and you may recognize that this is now the past, if anybody watched Back to the Future. But in the near future, well, let's think about what we can do immediately with the data at our disposal. So this is just some of the stuff that my group is working on. Partly, we're doing further characterization of the obscured quasar population with spectroscopy and X-ray follow-up, and my grad students and undergrad are working on this. In terms of how heavily buried they are, one of the things that we're going to try to do is expand these infrared to X-ray studies to very large numbers of objects over either wide field surveys, and I'll show you one example in a second, or the Chandra and NuSTAR whole archives, which is a really exciting thing that actually Andy Golding, who used to be here, and I have been working on software to do this really effectively. And so we want to see, basically, are all these things really Compton thick across the whole sky? Do we have a large fraction of them? And then lastly, in terms of the host galaxies and dark matter halos, we're really focusing on the clustering right now. And we want to expand these analyses to include more data and larger areas to try to get as much of the sky as possible. And also to develop some halo occupation distribution models that don't just tell us the overall clustering amplitude, but actually how quasars are distributed within their halos that may help us better understand these different clustering results that we have. And so this is stuff that Mike DiPompeo, he's doing some simulations right now to try to tease this out, and it's really, really interesting stuff. One example of one of these wide field X-ray surveys that we're doing is the expanded XBootes deep survey, which is, again, one of the legacies of Steve, where we're getting, we have these sort of serendipitous deep pointings in the Bootes 9 square degree survey, and we're getting some deeper pointings in around to try to make sort of more of a contiguous deep 40 kilosecond area, and we're going to then do a lot of these studies looking for obscured quasars in those areas and using these X-ray techniques like what I showed you before, what Sean Usman did on a larger sample. And hopefully, someday we may be able to expand this out even more. In the more distant future, basically a lot of what we need are just statistics, large numbers of objects. And so in the more distant future, Athena will, of course, has a wide field imager that can be very effective for this. There are lots of optical and near-infrared studies coming online that will let us get, for example, redshifts or other optical characterizations of obscured AGN. And so this is all of these get sort of progressively more powerful as you get farther and farther out in time from now. So things at least look exciting in the future. And then, of course, X-ray Surveyor would be extremely powerful for this kind of work. I'm really excited to think about what we could do with that. And so I guess I will end there and just say thanks again to Steve and to all of you for inviting me, and thanks again.
Questions for Ryan? Canada.
Of course, one of the most difficult things when you're comparing type 1s and type 2s is to actually match the sample.
Right, yeah, and we've talked about this a bunch before, yeah.
So can you remind us how you match the sample when you do the comparison of the cosmology?
Yeah, so what we do is, and actually this is a little bit easier when you get data that go out a little longer. So where's an example? Right, so here's a, come on. Right, so here's one of Chenting's SED fits. So the idea here is you have a galaxy, and then you have an obscured AGN that's sort of buried in there. The green is the galaxy. Here's the obscured AGN. You get some handle on what the extinction is. So you're generally not using the optical to get the luminosity. You're using the mid-infrared. But of course, you can still get some obscuration out to, say, 10 microns or so in the mid-infrared. And so what we do is work out how much AV there is here, and then when you calculate the luminosity, you basically calculate what it would be for an unobscured template. Now, this is not necessarily perfect because for two reasons. One is just getting the actual reddening out from the template itself can be problematic for the reasons I mentioned before. The other, just because it can be hidden in the galaxy and a bit degenerate. The other reason is that that assumes that your obscuration is actually just an obscuring screen. Whereas if you have a torus, and there's actually obscuration inside this torus, it can be much more complicated, and also the emission can be anisotropic. And so if that's true, then it may be somewhat challenging to do this. I think that given the SED coverage that we have here, and also some of the work that people have done that show that most tori do actually seem to be clumpy, so they don't have that much internal extinction. You're releasing the edges of, of optically thick clouds. That this is probably not a terrible assumption. And we always do the best we can to actually correct the luminosities. So if you just naively do a color-selected survey of quasars and calculate their luminosities, the obscured ones always come down a little lower than the unobscured ones. But then when you correct it, they tend to match pretty well. But this is always a potential concern. Oh.
I'm sorry. We're sitting side by
That's
side.
okay.
Welcome back. Sorry.
Class he told us comparing the XMM, Chandra,
Oh, right.
and the NuSTAR.
Yes, this one. Yep. Mm-hmm.
So, are you comparing the same sources? Is it really a bias that, with NuSTAR you see high columns than we observe and look at with Chandra and XMM?
What you do what happens, so they're mostly the same. This is a little more complicated than just getting all the sources in there. In fact, the ones that were observed in this program are just these 5 down here. But what happened was that you had these, if you do just a broad analysis of like a simple broadband spectral analysis of the NuSTAR spectra, of the Chandra spectra and XMM spectra of the type 2 quasars, then you get a distribution that looks like this. Some of them are Compton-thick candidates for other various reasons, like they may have an iron line or they may have a large ratio of X-ray to infrared emission, for example. And so, but it's very difficult based on just a simple fit to ever get out something that is Compton-thick because of the way that the shape evolves that I showed you before. So what this plot shows is the sort of naive Chandra results that come out, plus showing you which ones have other indicators that they might be Compton-thick. And you can see they're kind of all spread throughout this, right? When you go in with NuSTAR, the ones that appear to be Compton-thick based on sort of one of these indirect indicators do actually seem to be Compton-thick based when you have a more direct measure in the hard X-rays. And so what's happened here is he's basically just taken a lot of these and pushed them out to this Compton-thick bin here, inferring that the sample that we were observing, assuming that the sample we were observing was representative, which I think is reasonable based on the way that they were selected. So,
yeah, and also the ones which you really observed have actually larger columns because they are shifted.
right, that's right. Yeah, so some of these ones were ones that were potentially Compton-thick, right? And but again, a sort of simple spectral analysis suggests that they were maybe more like 10 to the 23. But then you look at them with NuSTAR, and it's clear they have to be more heavily obscured than that. So really what this is it's sort of, we just have now a more significant statistical handle on the fact that, or a more robust statistical handle on the fact that there are all these Compton-thick sources out there, when it might have been a bit ambiguous when you're only looking at lower energies. Does that not completely answer?
No, we should stop.
Okay. Yeah.
I'm just wondering about the impact of, if there is any bias if you take the population of cells and try to recover the background.
Right. Oh, right. Yeah. Right. I mean, one of the other issues is that the this sample is initially optically selected. So you have to, right? So you always have to think about what your initial selection is and whether or not that's actually representative. But the main point to take away from this is simply that you're getting a better handle on the fact that a lot of them really are Compton-thick.
Paul, I think I saw your hand before. Did you still have a question?
Yeah, I mean, I'm in danger of thinking out loud in public. But I was just wondering about, like, what do we know, if anything, about the supermassive black hole masses
Yeah, so that's a really good question. The answer is we don't know. We know hardly anything about their masses. There are some, I think, lightly reddened quasars where people have tried to get masses out using sort of modified virial techniques, and they tend to find that they're where you still can see the broad lines, and you tend to find that they have large line widths, and so yeah, they are probably pretty massive. But for the ones that are heavily obscured enough that you don't see broad lines, there's really no way to tell what the halo mass is at all. I mean, or sorry, what the black hole mass is, other than to infer some Eddington limit and at least put a lower limit on the mass, right? And so that's one of the things that we do. In fact, the interpretation for why there might be a difference in clustering that we presented in a couple of papers is exactly raising this point that maybe what's happening is the black hole masses are different sizes of the two. And that for the obscured sources, there's something about the way that you're identifying them above their host galaxy or something that means that they have to be they have to have a larger black hole mass, and then therefore are sort of catching up to, or that they have the same mass right now, but they're sort of catching up to the final mass that they will have in their halo. If you see what I mean, if they're growing very rapidly, it's all kind of contrived. There's not a good picture that we have right now for how to explain this. But certainly the masses are part of it.
Just relatedly, there are some objects that are mixed. They're right. They're like look heavily obscured in the X-rays, but unobscured in the optical.
Yeah.
For those, you could derive some estimate of a black hole mass.
Yep. Those are generally, we think what's going on is some kind of small scale piece of the torus that is producing that obscuration. There's a really nice paper by Andrea Merloni from let's see, end of 2013, maybe 2014, that did a really careful study of obscuration in different wavebands. And it looks like the ones that are X-ray obscured but optically not obscured are obscured by small-scale clouds in the torus. So there you could learn about the black hole masses, but they may not be the most interesting objects anyway. What you're more interested in is the one where the obscuration is not a torus, right? And so, yeah, it's a tricky game. I mean, basically this dust is just getting rid of all the diagnostics that you normally want to use. But one of the things that we're going to hope to be able to do, and this is now like big picture looking forward, is that my group, in particular my grad student Mackenzie Jones, is working on putting together a very simple galaxy formation model that includes sort of black hole growth in there, given in a very simple way. And then you can take all that. We understand galaxy SEDs pretty well now, and AGN SEDs. So you can paste. She's working on the X-ray part of things, but we're going to do optical and infrared too. You can paste the galaxy SEDs on top, and basically see what it was that you would get out. And so a lot of these selection effects, like bias towards more massive black holes, if you include a realistic Eddington ratio distribution, you'll see what that does to your selection. And so I'm hoping right now it's still really, this AGN selection game is very much a morass. Like it's complicated and we don't understand it. But I think we're getting to the point where maybe we can begin to get a sense of the bigger picture. So that's one of the things that our group is kind of aiming for in the future.
Could you remind me how far is the obscured quasars?
What's their distance? Most of the ones that we detect.
Pretty low redshift.
Well, not really. So I probably should have put a redshift distribution plot in there. Yeah. So these guys, most samples that are selected in the infrared peak around redshift 1. So they go up to, there are not very many obscured quasars at all in the very local volume. And so typically when you pick them just based on infrared photometry, you find ones that peak between, say, redshift 1 and 1.5 and go out to redshift 2 or so. And then, so for example, using more targeted techniques like in deep field observations, for example, you can find, like that example, redshift 5 obscured quasar that was identified in the X-rays. So there are examples out to higher redshift, but most of them live in the same regime that we find unobscured quasars, in the same redshift range, around 1 to 2.
Yeah, I was just curious because if the far distance quasars they can observe by the X-ray doesn't mean they can observe by the infrared.
Right. Yeah. It all depends on what the depth of your observations are, and also what.
The next question
Yeah.
is, so given the you're talking about the future, so what do you think for such kind of object, which band is the most suitable in order to get the deep physics from this picture? So what's the obscured,
In term-
are they related to the supermassive black holes, and or you just want to increasing the numbers and the statistics?
In terms of, yeah, sorry.
Or you just want to raise another. Just want to curious. So, what's the best tool in order to deeply understand this class of the obscured quasars? So,
The best
in
tool.
order to help us understand the host galaxies and the supermassive black holes,
Right.
I'm not satisfied with just increasing the numbers.
Sure.
Because we know the AGN's the unified model and for the ages, and we know the obscured the quasars for a long time. Yeah. Sorry.
Oh, that's all right. I would say the best tool, actually, one of the most powerful tools is mid-infrared spectroscopy. Not something that I work on at all, but it's real expensive and has been really expensive. There has been a lot of really good work, I didn't touch on it all in this talk, for other groups trying to characterize obscured quasars in the mid-infrared. And the nice thing about that is you can look for buried objects, you can look for high excitation lines that you would otherwise not detect in any other way. So there are some sources that actually don't look like quasars at all in any wavelength regime, but you see, for example, neon 5 in the mid-infrared, you say, oh, there's an AGN there. There are certain diagnostics that you can pull out from that in terms of the nature of the quasars. Other things are, I think X-ray spectroscopy is still very, very powerful if you can go really deeply in studying the nature of the obscuring material. So that's one reason why Surveyor would be so exciting, just having a large collecting area and getting a large number of photons. One other thing that also I didn't touch on here, but is potentially really exciting, is microwave line emission. If you're trying to look at really heavily buried AGN inside of a system with a lot of gas, then the excitation distribution of, for example, CO can actually tell you something about the AGN buried in there. So, and then you can see things about molecular outflows and all kinds of stuff. So I wouldn't really pick one particular waveband, because it all depends on which question you want to ask. But I think that sort of, for example, mid-infrared spectroscopy with James Webb, and CO with ALMA, et cetera. There's a lot of things that we're going to be able to do in more physical detail than we can do now, in addition to these large-scale large-scale statistical studies.
Okay, I think there are no more questions. Let's thank Brian again.
Back one slide. When you showed all the spectra, they went to like 0.3. This guy,
Right.
I was looking at these numbers.
This is one subset of them, and these guys are pretty
Yeah.
bright. So this
Okay,
is.
but these were all really low.
These are really low redshift, yeah. So these are
That's
ones.
why I
These
thought
ones were. This is the low redshift end, but it shows the lines a little better. That's why I picked this one. The other thing is that salt is not all that sensitive.
Yeah.
So we had to pick things that were optically brighter